In this video, we're going to talk about 2.6 Day 2, which covers more information about competing function model validation. In 2.6, the learning objectives include constructing linear, quadratic, and exponential models based on a data set. It's important to remember that the data set is not going to be a perfect fit for these models, and so we are going to have to choose a model that best fits the data. We can do that based on context and the applicability of our types of functions, or we can do it based off of information like residuals. So the second half of the learning target is to validate the model, so to be able to explain why you chose a specific model and defend your argument with evidence. In our warm-up, we have a scenario in which an exponential regression was used to model a data set. We don't have the regression equation or the data set, but what we do have is the residual plot for the model. Based off of the residual plot, the question is this model appropriate? And you need to justify your answer. So whether you say yes or no, you need to have some sort of support for that. I'd like you to pause the video, write down your answer, and then press play to see if you are correct. What we're looking for is whether or not there is a pattern within the residual plot. The more random the residual plot, the better the model is for the data set. We would say that yes, this model is appropriate because when we look at the residual plot, the points seem to be scattered very randomly. There's no pattern. The dots aren't organized in a particular way. The more random the residual plot, the better the model is for the data set. When we create these models, whether they're linear, exponential, or quadratic, or some other polynomial, we use those models to predict the values for the dependent variable given an independent variable. So we're predicting outputs given a certain input. It's important to remember that this is just a prediction. It's not going to be 100% accurate. So when using a model, it's important to remember that this is only a predicted value. So our goal is to get close to the real value, but it's unlikely that we're going to be exactly spot on. If we use the input value from a known data point to find a predicted output value using our model, we can compare the predicted value to the real value and get something called the residual. And the residual is the difference between the actual, the real output, and our predicted output. The residual is a numeric value that we find by taking the actual value minus our predicted value. So it's the difference between them. So now we're going to take a look at some examples. In this first example, we have the scenario that a weight of a newborn baby can be modeled by a linear function for the first 4 months after birth. Selected values of the weight, W of t in kilograms, of a particular newborn baby are given in the table to the right, where t represents the number of months since birth. Using the table, the first thing that we're going to do is find a linear regression model. So I would like you to pause the video, use your calculator, enter this information, this table, underneath the Stat Edit button, and then go back in, hit Stat, go over to the Calculate menu, and choose the linear regression model that would fit this data set. You may have noticed that there are 2 options underneath that Stat Calc menu for linear regression. It just flip-flops the order of the slope and the y-intercept. You can write it either way. You can choose either option. The slope should be 3.34 and the y-intercept should be 0.8. The next thing that we're going to do is we're going to use that model to predict the weight of the baby 2.5 months after birth. Okay, so we're looking for this value that would be in between the 2 and the 3 inputs that are in our table. So using our model, our input is going to be 2.5, and we're looking for the output. So I'm going to plug in 2.25 in for x, or t if you stuck with your input value of t, and our output is going to be about 5.34. Now in part C, we're going to calculate a residual. It says that the actual weight of the baby 2.5 months after birth was 5.5 kilograms. And now we can use that to compare to our prediction since they're for the same input. So it says what is the residual for this weight? Did our model underestimate or overestimate the weight of the baby at 2.5 months after birth? So the residual is a numeric value. It's the difference between the actual and the predicted value at the same input. Actual value is 5.5, predicted value is 5.34. If we subtract that, we get a positive 0.16. Okay, we can see that our predicted value is less than the actual, so this means that we underestimated what the real value was. If we think about what the residual plot would look like, our residuals are all going to be close to 0. We would plot this point with the input being the time, or the months in this case, and the output being the residual value. So the output is going to be that difference. So it would be positive above 0 with an input value of 2.5 on the input axis. So we'd have a point about here. The full residual plot would include more points. We would have a point for each of these values from our table. All of these actual values, we could make a prediction for that same input based off of our model and then calculate the difference between them. So we'd be able to add at least 5 more points to this residual plot. So here are some more examples of full residual plots that show all of the residuals for a data set. And again, we can use that to determine if a model is appropriate or not. If a model for a given data set is appropriate, the residual plot should appear random. You can also say without pattern. So the less pattern there is, the more random it is, the better or more accurate your regression model is. So we can see the randomness within this top example. The points are scattered, both above and below 0. The 3 that are below would be inaccurate regression models because there's clear patterns. We can see in this first graph how the dots kind of go down and come up. They almost appear quadratic. In the second scenario, they appear linear. In the third scenario, they kind of go down and come back up, and then we have a section that goes up and then comes back down, almost like there are 2 different patterns within there. And it's kind of counterintuitive. Despite having a pattern, it actually means that it's not appropriate because there's some sort of consistency within our predictions. Either our predictions are consistently too high or they're consistently too low, which means there's a different model that's going to be a better fit for our data. We're now going to look at a couple multiple choice questions that would be examples of what you might see on the AP exam. So this next one says, an exponential regression was used to model a data set. We don't have the regression equation or the data set, we just have the residual plot. It says the residual plot for this exponential regression model is shown below. Which of the following is the best conclusion about the appropriateness of the exponential regression model based on the corresponding residual plot? So the multiple choice questions are whether or not this is appropriate. So it is or isn't appropriate, and why. So I'd like you to pause the video, Decide whether this is an appropriate model or not, and then select the correct option from the multiple choice that has the correct justification with it. All right, because there's seemingly no pattern within this residual plot, this model is appropriate for the data set, so I eliminated A and B right away. Between C and D, C would be the correct response because the argument that supports that answer is that there's no pattern. Here's another example. It says Mr. Brust started a new online business selling Brust merch. He made estimates about his revenue and used an exponential regression to develop a model for his sales over time. The figure below shows the graph of the residuals of the exponential regression model. Which of the following statements about the exponential regression is true? So, same multiple choice options. Is it appropriate or not, and why? I'd like you to again pause the video, think through these 4 options, and select the appropriate response. There's a clear pattern within this residual plot. It almost appears quadratic, so this is not a good model. So I'm looking between options C and D. The correct choice is C. The reasoning there that supports my answer is that there's a clear pattern within the graph. Option D is not correct because there's no exponential pattern. An exponential regression model should not have any pattern at all in its residual plot. In example 3, you're going to have another opportunity to create your own regression model. It says the altitude of the sun is simply a measurement of how high it appears above the horizon in terms of an angular measurement. On Halloween, Mr. Gomer does his best to measure the sun's altitude throughout the day. The measurement in hours H since sunrise and the angle A in degrees are given below. So we have our input in hours and our output in that angular measurement of altitude. This question has 3 parts. In the first part, it says find a quadratic regression model using your calculator, and it says round to 3 decimal places. We have to be careful, although we're going to give our answer written down on our answer sheet rounded to 3 decimal places. We want to store this equation underneath that y equals button so that we can use the non-rounded equation to make predictions. We never want to use the rounded equation to make predictions because it's not going to be as accurate. In part B, we're going to use the model, again, using the stored non-rounded equation to calculate the residual at an input of 10. So not looking at the table, but rather using our equation that we made. And then in part C, we're going to analyze that prediction. Is that prediction an overestimate or an underestimate of the actual value? And we're going to need some sort of calculation to support that. I'd like you to pause the video and give these 3 a try, see what you come up with, see what questions you have. All right, so using the calculator, our equation should look like this: negative 1.458x squared plus 16.164x minus 2.195. If your equation does not look like that, go back and double check your tables. You probably misentered something. Using that model that I stored in my equation y1 in my calculator, I'm going to predict the residual at an input of 10. You can do that by typing in y1 of 10 using parentheses. You can trace it on the graph, or you can use the table. You should get an output prediction of 13.630. To support our choice in part C, I'm going to calculate the residual by taking the actual value from the table, which was 12, minus my prediction. I get a result of a negative 1.630. The fact that it's negative tells me I overpredicted. And on my residual plot, that point would be below 0. Here's our last example for this lesson. It says students from an AP pre-calculus class were brought to the gym to shoot free throws, but only the students with little to no basketball experience were allowed to shoot. Each student was given 60 seconds to shoot as many free throws as possible. A regression model was calculated with the student's height in inches as input values and the number of shots made as output values. The residual plot for the regression model and the data points is below. Part A says the given residual plot has a point labeled P, which is right here, at the coordinate 62, 4.7. It says, what does the point P indicate in this context? Well, we know that the coordinates of this residual plot give us the input and the residual. So P is analyzing the data for a student who is 62 inches tall. The fact that our residual value is positive and the fact that P is above 0 tells us that we underestimated. So we can say that for a student who is 62 inches tall, the model underestimated the number of shots by 4.7. Next, it says the point labeled Q, which is right here, is at the coordinate 74, negative 2.4. What does point Q indicate in this context? Again, our input value is the input from the original data set, so we're analyzing a student who is 74 inches tall. The output of the residual plot is the residual, so we have a negative residual. We can also see from the residual plot it's below 0, which means this is an overestimation by 2.4. Often we will have to justify or explain our analysis. And so the arguments that we can use for an underestimate is that our residual is positive or the point is above the x-axis on the residual plot. When we are defending our answer of an overestimate, we would say that our residual is negative or the point on the residual plot is below the x-axis.